and it killed a little bit more than 1.5 million patients. Why, in an era where we have antibiotics that work? Well, one of the reasons is people don't take their antibiotics. They get prescribed antibiotics and then they desist. TB is one of these diseases where you have to take your drugs for about 8 months, 6 to 8 months. And when a patient comes in, they take their drugs the first month immediately because they're dying. They're throwing up blood. It's just a horrible disease. And then at 1.5, they stop taking their drugs because they feel better, and the only thing that they sense is the side effects from the drugs. And so they need people to help them and be coached throughout the process. And the WHO's current standard of care is something called DOCS, which basically is somebody that goes to your house, checks up on you, writes it on a notebook, and goes home. Or you go to the clinic. And that works great in a country like Japan, or America, or even Mexico. The problem is that in other countries, the community health workers may not show up to work, the person may not want to go to the clinic. There's a disconnect in the availability of care with these workers. And after a while, again, the patient stops taking their drug, the treatment then develops multi-drug resistance TB, and your treatment cost goes from $120 to around $900. In a country like Haiti, where people spend less than $100 a year inpatient, that's basically a death sentence. So taking drugs is an important part of treating TB. And when they came to us with this design challenge, I was like, this is a really boring project. I mean, these are basically pill boxes that you buy at the pharmacy. But we came up with a system called XLTB. And the idea here was to try to trick people into taking their drugs in a sustainable manner over 8 months. And what we do is we use diagnostics and economic algorithms. So we had to use a very multidisciplinary team. And what happens is the patient takes their drug, and then they take a test. The test is developed in about 5 minutes, and it develops a random code that we know beforehand. They send the code over SMS, and they're given a prize. In the case of TB, they're giving cell phone minutes. And now they have an incentive beyond the fact that they're going to live in month 8 to take their drugs, which is they're going to get a really big prize of cell phone minutes at the end of the week. So in places like Nicaragua, cell phone minutes are prized. In places like Japan, I think we would probably give away Wi-Fi codes or something like that. If I had to, yeah, at least. So that was one example. It's allowed for a very interesting notion of how to design for the developing world. One of the things that we focused is making sure that the majority of the innovation doesn't happen at MIT. The test left half done. When it left the lab, it went to Nicaragua, but we worked with local scientists and they perfected the TB for specificity and sensitivity, and now we're manufacturing in Managua, inventing new types of liquid handling equipment to automate the process, and then exporting these tests to Pakistan, where there are 1,600 patients under clinical trial. We're looking at different form factors, such as QR codes and patches, and other ways of detecting the signal, so that you don't have to just punch in the code. And to the notion of triple up technologies, this is one of those examples where it comes back and surprises us. We did this specifically developing it for the developing world, and now we have companies in America saying, you know, we have heart patients that need to take their drugs every day. We have patients that have mental illness that need to take their drugs every day, and we have issues, and we need it. Will this work for them? And so now we're trying to work with drug companies, identifying biomarkers that we can use the same type of method, but for drugs in America, which we later found out that compliance is a $300 billion problem in America. So it balances out. One of the things that I should point out when you look at things like this is, don't design it immediately thinking, I'm going to design it for Nicaragua, but I'm going to also be thinking about what Pfizer's going to want. Focus on the design challenge for Nicaragua first. Keep the possibility of trickle up in mind, but don't let it warp your sense of design. Because otherwise what ends up happening is you're really going to design for Pfizer. And then you're going to let the Nicaraguan solution go. And It's one of those things where you end up with neither the Pfizer solution well or nor the Nicaragua solution well. Another series of devices are a lot of microfluidics projects looking at sepsis. We have tuberculosis breath tests with collaborators at Draper and CIMMYT. We have something called the glucovent, which is a way of delivering glucose tests at a community center, very similar to the vending machines that you have here, but in our case, our vending machines deliver a glucose test. We use Google Earth for tracking disease surveillance and doing epidemiological studies. This is how they used to do it before, just very manual, labor-intensive maps. And through Chris Olson, we're developing something called the Car Parts Incubator, which is taking old, discarded parts and developing a methodology so that people in the developing world can make incubators for babies using car parts. They have all the elements that you need for making. They have heating systems, they have cushions, they have controls, they have lights. A lot of haptic devices for balancing. Some OBGYN tables that can be carried in the middle of nowhere and then deployed so that a mom can deliver safely. This is a device that we're developing for the blind so that they can have better spatial awareness of what's going on around them. A lot of wheelchair design, very similar to the work done in Caltech. This is work being done by Amos Winter in the lab. And the project that I get most excited about is the MEDIC project, where we're being true to ourselves about empowering our users. And we're going to Nicaragua and Ecuador, and what we developed is a series of kits, very similar to Lego kits, if you will, or constructs or erector sets. But in the end, the result is not a car or a robot, it's a medical device. So what we learned is that, again, doctors and nurses are hacking a lot of these different devices. They don't know how to put things together, or they know what they want to put together, but they get stuck in the junctures, or they get stuck in the fact that they don't know about formal design processes. But they know what they want, and they know what they want before we know it. And so instead of having us fly down there every week and be embedded or move to Nicaragua, we're trying to give them tools because they don't have machine shops, they don't have the laboratories that we have, but hopefully they can have something in a box that allows them to innovate. And the kits allow them to do about 7 different things. We have one kit for drug delivery, diagnostics, even lab-on-a-chip devices, prosthetic design with Ken Endo at MIT, and imaging, for instance. And this is one of the earliest lab-on-a-chip devices that our students made in Nicaragua. And I'm not sure if I put the machine here, but we were able to transfer the ability of a clean room facility for using microfluidics to something that costs around $350 using a process called xerography. These are some of our Nicaraguan students showing us how they're designing auto-disable syringes and communicating over video conference with mentors at MIT. And here they are using diagnostic know-how and how to make simple colorimetric tests. And if you notice, I'm not sure if this is going to work, but yeah. Can you see this? Can anybody guess what this is? Clearly they're using it, they're drawing the reagents and they're using it over here. But if you recognize this pattern, this is coffee filter paper. Because we ran out of Whatman paper. And the reality is it works just as well. Melita brand works really well. And we're transferring these, very simple abilities of how to make the materials and devices not just affordably, but using some of the local ingenuity. How do we get there? I'm going to close with this very quickly. A lot of people say, how do you come up with your ideas? How does the lab just, we've had people come and tell us, do you have people sitting in a room just thinking all day long? Ken does that. No. But no, when we look back and we try to identify all these processes that allow us to come up with these ideas and allow, more importantly,